background is in mechanical engineering, so this picture makes me very excited. I'm very much looking forward to this. So we'll get started here. So our lesson plan for today. So we're going to start by reviewing forces and pressure, although the formatting on that is a little strange, that's fine. We're going to move to a small hands-on activity. Then we're going to learn some new information about fluid pressure and hydraulics. And finally, we're going to be doing a hydraulics demonstration at the very end of the class today. So that's just our sort of basic layout for the day. We'll get started with a quick review. Who can remember what a force is? I know it's up on the screen. It really wasn't supposed to be like that, but that's totally fine. A force is a push or a pull, and some important things to remember about it is that it has both a direction and a magnitude. So, direction is which way the force is pushing or pulling, and usually in science or engineering, when we're talking about forces, we like to denote it with an arrow, just so we can indicate where that force is going. And then it's also got magnitude. So I like to use big arrows if it's a big force, like this big strong man up here. And I like to use small arrows if it's a small force, like, I can't remember what her name is. Is it Agnes?
I think it's Agnes.
Agnes? Okay, fantastic. Not that that's important, that won't be on the test. You just have to remember big force is indicated with big arrows, small force indicated with small arrows. And so magnitude is how strong the force is. Usually we measure that in pounds or newtons, depending on if we're working in imperial or if we're working in metric. Does anybody remember where is imperial usually used? Do you know what I'm talking about when I talk about imperial units? Yeah.
In like the States?
Absolutely. The States and Laos, I think, are the two countries that still use imperial, but pretty much everybody else uses metric, so measuring in newtons, measuring in meters, measuring in grams, liters, that sort of thing. But we also use a strange mix here in Canada. We measure height in inches, but distance in kilometers. We measure weight in pounds, but we measure, I can't think of another example right now. Anyway, we're going to learn a little mishmash of the two, imperial and metric, just because we do tend to use both here in Canada. So, a little more about forces. Again, the formatting is a little bit strange here. I'm a little upset about that, but hey, what are you going to do, right? So, just to give people a sort of an idea, because everybody knows sort of what a pound is. Usually you measure your own weight in pounds, like I'm about 240 pounds. So I have a good idea of like what 1 pound or 100 pounds or 1,000 pounds might look like. But I'll be honest, I always have a hard time remembering about how much a newton is. So 1 newton is about the weight of a basketball, and if you compare that to a water bottle, which one do you think is bigger, or which one do you think has more weight between the water bottle and the volleyball? Hands up for volleyball.
Is the water bottle full?
Yeah, it's a full water bottle. Good question. Yeah, and so since nobody put their hands up for volleyball, who thinks that the water bottle is heavier, has more weight? Yeah, absolutely. So it's a little hard to compare the two, but you start to see the difference when you get up to 100 pounds versus 100 newtons. So 100 pounds is about what a 13 or 14-year-old junior high school student would weigh. Whereas 100 newtons is about how much a Thanksgiving turkey would weigh. It's about 22 pounds-ish. That's for a really big one. And then 1,000 pounds, we see an even bigger difference. 1,000 pounds is about a smart car, maybe a little bit less. Whereas 1,000 newtons is almost exactly the weight of Chiefs quarterback Patrick Mahomes. So I had a lot of fun making this slide and researching how much stuff weighs. So that's just to give you an idea of how much a newton is versus how much a pound is, because I think that's going to be very important as we go into our next few slides here. So just to review, you should have covered this in, I believe it's grade 6 in the current curriculum and grade 5 in the new curriculum, about air pressure and how force can act over an area. So pressure is a measure of force acting over area. So we have our force indicated by our arrows, right? And it's acting over this gray area, also referred to as the unit area A. So if you've got your math brains turned on, your pressure is equal to your force over your area. And it's a really simple calculation, and there's really a lot that we can learn from it. In metric, pressure is measured in pascals or newtons per meter squared. So usually the steps are you figure out your weight in newtons, you figure out your area in meters squared, and then you divide your force by your area. In imperial, we measure in pounds per square inch. So again, figure out the weight applied in pounds, and then you divide by, then you find the area in square inches. You go force in pounds divided by area in square inches. And that's our formula right there on the right. Okay. So, in previous grades, you talked about air pressure, how if, for example, you talked about Bernoulli's principle maybe, and how fast-moving air can exert less pressure, and slow-moving air can exert more pressure, and that's how a wing works. But it turns out that solids actually apply pressures too. As long as you have a force and an area, you can get your pressure. So freestanding solids only have one force. So you have your weight, or also known as the force of gravity, that's acting on this cylinder here. And if we just take away the entire body of this cylinder here and just focus on what's important to us for pressure calculations, force and area, we can actually calculate our pressure based on that. So again, the force of gravity is the force that's pulling the mass of that solid down, and it results in a downward force on that area that it's standing on. And in that way, we can have solids that can apply pressure as well, not just gases, not just liquids. So, for example, and at this point in the class, I would sort of pose this question, give them a little bit of time to think about it, and not necessarily have them write anything down, sort of visualize how they would go through this problem. But for the sake of time here, we're just going to run through. So here's an example of how to calculate pressure in PSI, or in those imperial units that are usually used in the United States or the house. And so you're going to start off with a 3-pound textbook, width of 9 inches and a length of 12 inches that's lying on a table. So can anybody tell me, what in this sentence here do you think is important information? Or maybe I'll point stuff out and you can show me yes or no if you think it's important. Okay, so what about 3 pounds? What about this 3 pounds? Do you think that's important to our pressure calculation? Yes, okay, that's fantastic. That's great. What about the fact that it's a textbook? Do you think that's super important? Not really. Maybe the only piece of information that we should get from that is that it's probably a rectangle, right? And that'll help us figure out our area. But then we see a width of 9 inches and a length of 12 inches. Important? Not important? Very important. Yes, fantastic. I'm seeing lots of thumbs up. That's great to see. So if we have that information and we want to figure out how much pressure is the textbook applying on the table in our PSI, then we just go to our formula. We're trying to find pressure, and we have our force and we have area. So our first step then is we're determining the force, which is given in the prompt. It says that it's 3 pounds. Next is to determine the area. So we would take the information given, which is 9 inches by 12 inches. And as we learned in math class, to find the area of the rectangle, we just multiply the two. And so that gives us an area of 108 inches squared. And again, formatting is the bane of my existence. But step 3 is calculate the pressure. So we take our, as seen up in the top right here, in order to find the pressure, we take our force, which is 3 pounds, and divide it by, let's see here, 108 inches squared. So 3 pounds divided by 108 inches squared equals 0.0278 pounds per square inch, or 0.0278 psi. How's that seeming for difficulty? Are you following along okay? That's not feeling too overwhelmed? Fantastic. Okay. And here's just the same example done in metric. I'm not going to fully go through this, but it goes through the same process of finding the force, determining the area, and then making that pressure calculation. Okay. Okay, well, something horrible must have happened transitioning between Google Slides and PowerPoint. But anyway, although the answer has been given away here, we can still go through why these other answers aren't correct. So, as an aside, I was really intrigued by the idea of creating questions with good distractors that are able to identify where a student went wrong. So, for example, we have our practice question here, which has a rectangular prism weighing 100 newtons is lying on a scale as shown in the picture to the right. How much pressure is the prism applying to the scale in metric units? So the answer is 5,681 pascals. But if we go through reasons why these answers are wrong, of course these bottom two units are wrong because our question is asking for it in metric units, right? And of course PSI is imperial, so that's a completely different number system. Although the student might have gotten the right number answer, we want to try to identify that they still have that misconception about metric and imperial, right? And then if we go through with this other question and students ended up with answer B, what I want to do is I want to prompt them. Did you remember to convert to meters, right? Because if they divided 100 newtons by 8 centimeters by 22 centimeters, 8 times 22 is 170 something, 176, something like that. And if they did that, then they would end up with a much smaller number that they might have selected. So it's trying to weed out sort of the different misconceptions or errors that a student might make during a question like this. Okay, and so this is our activity. Again, for time's sake, this is we aren't actually going to be doing this, but I thought this was a fun one. It's actually something we did when I was in grade 8 with Mr. Dochuk in my Science 8 class. So it's a question of how much pressure do you generate? You're going to take a piece of graph paper, and like I've done here, you're going to put your foot on it, you're going to trace your outline, and you're going to count the number of squares covered by your footprint, and that way you'll be able to get like an exact area for your foot, because your foot's not regularly shaped. There's little bumps and ridges and stuff like that. So that area combined with your known weight in pounds, you can figure out how much pressure you actually generate as a solid, as we've been talking about. And then during that activity, I wanted to give them some prompts for questions that they could think about during that the students could think about during this activity. So I want you to try to estimate how much pressure you think you're going to apply. Do you expect a big number or a small number? How big or small, and why? These next two are sort of conceptual questions. How would your pressure change if you wore larger shoes? How would your pressure change if you wore smaller shoes? And then this question here addresses, would you expect your pressure number to be bigger or smaller than Mr. Wags? Explain why. Sort of getting you to think through, like, okay, Mr. Wag, he looks like he might be able to apply a lot of force, but he's also got really big friggin' shoes. So, how do you think that impacts your pressure versus his, and how much of a difference do you think there is?
If you wear heels, I'm going to apply more pressure.
Yeah, exactly. Yeah. I didn't wear my science stilettos today, so I won't be applying nearly as much pressure.
In there.
Yeah. Yeah, I know, I forgot. Yeah, it's perfectly with this shirt too. Okay. So yeah, that more or less wraps up the activity. And so this question, again, is another one of, I want you to think a little bit about this. Take a couple seconds. And I want to know, how can the pressure applied by a solid be increased? Take a couple seconds and think about that pressure equals force over area formula. Turn on your math brain a little bit, and we're going to go through these one by one. So how can the pressure applied by a solid be increased? Select all that apply. So does the pressure applied increase when we increase the weight of the solid? Show me thumbs up or thumbs down. Wonderful, looking good so far. Yeah, absolutely. So that's correct, because if we're increasing the force on the top of that formula, then that number is going to get bigger, right? What about B? Increase the area on which the object is applying force. Does that increase the area? Show me yes, no. No, excellent. Some fantastic future mechanical engineers here. Because if we increase the area on which the force is applied, then that's dividing by a larger number, right? And say we had a force of 100 and we divided by 10, we would get 10. But if we increase the force, or the area rather, to 20 and divide 100 by 20, then we would get 5. So we're actually decreasing the pressure. And then does decreasing the weight of the object increase the pressure? Yes or no? Fantastic. And then decreasing the area is the opposite of this one. So that one will actually increase the force. Fantastic job. Okay. So I don't think there's a whole lot left. I'll just quickly check. And formatting. Okay, so this leads into a conversation about hydraulics. We have now learned how solids can apply force and pressure, and so we're also going to learn how liquids and gases can apply forces and pressure too. So, reviewing from grade 7, the particle model of matter. All matter is made up of solids, liquids, and gases, as you can see in the top right corner there. And each of those is made up of teeny tiny particles, and they are always moving. So in gases, that's pretty easy to understand. We felt wind. There's lots of space for the particles to move around. In liquid, they're more tightly packed, but they are still moving past each other. We can visually see that if it goes like a swimming pool or something like that. And finally, we have solids, which are very tightly packed and constantly vibrating back and forth. And also remember that fluids and gases take the shape of whatever container they're in. So regardless of what shape these glass tubes are in, the liquid has formed to that. And here the gas is taking the shape of the balloon. So in fluids, pressure can be applied 2 ways. So liquids and gases apply pressure by pressing against the walls of their container. So every time a teeny tiny particle of gas hits the side of its container, if it's like the walls of this room or the floor or the ceiling, it's actually creating a little teeny tiny bit of force. A little teeny tiny bit. But if you get a whole bunch of them working together, then you start to get more and more force. So for every little collision that happens in a liquid or a gas, you're generating that little bit of pressure. The second way that objects or liquids and gases can apply pressure is they can actually apply pressure because of the weight that is sitting on an object in the fluid. So, for example, based on this second point of pressing on any object submerged in the fluid, which one of these 3 do you think has the most pressure on acting on it? Do you think it is A, B, or C? Let's see hands for A, B, C. Wonderful, fantastic. Okay, that's really good. I'm very glad to see hands going up for that. And here's a little visualization. So again, representing forces with arrows. Inside the fluid, the fluid is trying to push in all directions. So it's sort of starting from the middle here, and it's pushing out against the side, it's pushing against the bottom, pushing against the side here, and it's pushing up against that yellow object there. In the second, again, you've got pressure acting from all sides, so on the walls of the container as well as on the orange body itself. And you've got a little bit on top that is weighing down on that orange object and applying pressure in a stack down like that. And finally, with the green object, you've got lots of water on top. And as that column sort of increases, then there's going to be more mass on top of that object, and as a result, more gravitational force, and as a result, more pressure acting on that same area. So anyway, for the sake of time, I'm going to wrap up. With one last question, I suppose. When do we feel fluid pressure? Are there any examples you can think of in your own life or experience? We won't discuss, but does anybody have any ideas off the top of their head?
Swimming.
Swimming? Absolutely. So this is, again, a further explanation of how, if you imagine all the air stacked on top of each other, on top of your head, it's a stack about 700 kilometers high, and all that air together weighs about 13 psi. But anyway, feel changes in fluid pressure, dive into the bottom of the pool, you can feel it with your ears, climb the mountain, that decreases the pressure pressing down on you, and finally going up the mountain increases pressure because all the air is at the top. Anyway, again, I said I would wrap up, so I'm going to end there. Thank you all so much, and good luck with the rest of your term.